Okay. All right, so Unit 5, Day 1. I don't have access to this video, but I'm going to talk about it as if I did. So here's the idea, I think. You're going to start with some air in your lungs, let's say here. You're going to inhale, exhale, and then when you exhale, you push more out than where you started. Inhale, exhale. All right? So here's the inhale time from the beginning. Here's the exhale time, and then the inhale. I'm assuming we didn't start fully exhaled at the beginning of our story. So let's just make it up. So let's say we have 2 minutes inhale, or 2 seconds inhale. Let's say it's from the bottom to the top, that's 2 seconds, and then 2 seconds exhale. And we have 4 seconds for a complete breath. And in the video, they probably talked about the volume of air, where at maximum, minimum amount of air in your lungs. And so one full breath cycle, let's say we start. Let's say we start here. Exhale, inhale, and then we start over from these two. So here's what we call one full cycle. Okay? Exhale, inhale. I can do this hopefully over and over again for a long time because we want to be able to breathe. And so we can count the number of cycles or number of repeats we have in, let's say, 2 minutes. And the video, I'm sure, talked about more like that, but that's where we're going. We're going to have this thing that's going to start over and over and over for a particular period of time. Period of time, this thing is what we call periodic. For that periodic table in science, the atomic structure starts over again each row that you go down the periodic chart. So a periodic function, maybe it is something like this. It has a max, it has a min, and more importantly, it has a cycle. Let's say we go from here to here, and that's one cycle. And here's what's going on, right? If I go from here, it goes up, down, and up again, that's one cycle. And then it copies it again and again here. It's like a clone. Each cycle is a clone of the one before it. So here, you can take any starting point you want to. Let's say here. And then it ends here, and then it repeats here. So then we could say that the period is 4. Now somebody else says, no. I want to start here and go here, and then repeat. But look, it's still 4. It doesn't matter where you start as long as you repeat that same pattern. Domain, how far left and right? We have arrows, so negative infinity to infinity. Range, bottom to top, from negative 2 to 2. Domain, range. The x-intercepts are at -5, -3, -1, 1, 3, 5, etc. Now, there's more than that because this keeps going. What if I said this? Okay. I'm going to start at 1, and then I'm going to add 2 more for the next one, and 2 more for the next one, and 2 more for the next one, and I'm going to do this forever. So if I do this, 1 plus 2k. So if k is 0, I get 1. If k is 1, I get 3. If k is 2, I get 5. If k is negative 1, I get negative 1. If k is negative 2, I get negative 3, etc., don't I? Now, if I plug in a half or 0.7, I won't get these numbers. But k is a variable. I can plug in anything, but I want these numbers. So I better tell k, you can't be anything. K, you have to be in the set of integers. Positive and negative whole numbers only. Because otherwise, this variable can run crazy. So the x-intercepts are in this form. Now, what if someone else says, no, I want to start at negative 1? It doesn't matter. They're still 2 away from wherever you start. You can start wherever you want to. Now, they want you to go out to 134. I don't think you want to do that. So let's make an observation. When x is 0, y is 2. When x is 1, y is 0. When x is 2, y is negative 2. When x is 3, y is 0. And when x is 4, we're back up to 2. And then it repeats over and over and over. I have an idea. Let's take 134 and divide by 4. 4 goes into 13 3 times. 3 times 4 is 12. Subtract, bring down. 4 goes into 14 3 times. 3 times 4 is 12. Remainder 2. If we had come up with a remainder of 0, wouldn't that mean that I would end at the same place I started? But with a remainder of 2, doesn't that mean that I'm going to end 2 from where I started? And so that the answer is negative 2. And here's the idea. When I divide by 4, the biggest remainder I can get is 3, right? Because if you get a remainder of 4, you know that you chose this number wrong. So our remainders tell us what the answer is going to be if I have a function that repeats over and over and over within a certain period. Describe the symmetry. Do you see that our graph has a middle of the y-axis? So it's balanced on either side of the y-axis. And so it has y-axis symmetry. So it's balanced to the left and to the right. Sometimes we call that an even function, because y equals x squared is the poster child for an even function. Well, if it's symmetric to the y-axis, if I go to the right 134 and I get negative 2, if I go to the left 134, I'll bet you, we also get negative 2. The graph below is also periodic because this portion is a Xerox copy of this portion, is a Xerox copy of this portion. So the period is 1, 2, 3, 4, 5, 6. The domain goes forever left and right because of the arrows. so that we go from negative infinity to infinity. But since it's an open circle here and here, we have holes. So we could say except, but now we have a problem. You want to list all the holes, like -9, -3, 3, 9, and go ... You could do that. But how about if we say except x, or we could say x cannot equal, and pick one of them. Like I'll pick -9, and then every 6 we skip. So plus 6k, there it is again. So if I add 6, I'll get to another number I'm going to skip. Add 6 again, add 6 again. But right, k has to be an integer. A positive or negative whole number. I can't deal with fractions or decimals. The x-intercepts are -6, 0, 6. Here we go again. So x-intercepts are going to be, let's start at -6. And how far away is the next one? 6 and 6. And so 6k, every 6k, k has to be an integer. That's where all the x-intercepts are. All. Now, this graph is not symmetric to the y-axis. It's actually symmetric to the origin. So if I go 3 to the right, I'm at 1. If I go 3 to the left, I'm at -1. That's what we call an odd function, or a function symmetric to the origin. So if I change the x to a -x, I change the y to a -y. So let's try this. If I take the 530, the positive one, and I divide that by 6, because that's our period, 6 goes into 53 8 times. 8 times 6 is 48. Subtract, I get 5. Remainder, bring down the 0. 6 goes into 50, 8 again. 48, remainder 2. So that the 2 gives us a value of, let's say, 0.6. But on the other side, a -2 will give me a value of -0.6. Well, the same is going to work for 530 and -530. The 530 is going to give me the positive 0.6. The -530 is going to give me a -0.6. So as we said here, the symmetry is respect to the origin. If I stand at the origin and reach out with one hand and then reach out with the other hand, standing at the origin, I will hit something on both sides of the graph. Origin symmetry, or it's an odd function. The poster child for an odd function is y equals x cubed. But don't learn that odd functions have an odd exponent, because this graph doesn't have any exponents and it's still odd. So we just said that the value of 530 is going to be a positive 0.6. So here they are. That even function is symmetric to the origin. So if I feed the function a negative value, it'll be the same as the positive value. The same y value. But in an odd function, if I feed it a negative x value, I'll get this y value, But if I feed it the same x value but positive, I'll get the same y value but positive. Or they'll be the opposite. So for these, I plug in 2 or negative 2. It doesn't matter. That's an even function. If I plug in 2, I get a half. If I plug in negative 2, I get negative a half. They're opposites. That's an odd function. Here I plug in 2. Let's plug in 4. I get 2. I plug in negative 4. I get undefined. That's neither one. So you go ahead and verify that these other answers are correct. Now you saw me in the previous examples plug in 2 and negative 2 to try to answer the questions. Okay. But plugging in 2 and negative 2 is not a proof, because if you want to prove, you've got to plug in all numbers and show it's always going to happen like that. Well, to do that, what you do is you plug in a variable. You plug in a variable, it represents all numbers. Okay? So, if I take this function, replace x by negative x. I square it and I get x squared. If I replace x by negative x and I get the same value as the original function, it's an even function. Since I used x and negative x, that proves it for all numbers, because the x and negative x represent all the numbers I could have chosen. Same thing here. I replace x by negative x, and I get negative 1 over x. Well, I look at the original 1 over x, and the answer I got was the opposite of the original. If I get the opposite of the original, it's an odd function. Again, you do the same thing for these. I'll show these so you can see what I did, and you can see if you can verify the same thing I did for the others. Okay. Example 6. Is this even or odd? Well, let's see. If I plug in a negative x for x, well, a negative to the odd power is negative. A negative to the odd power is negative, but the 3 drops down. This is not the opposite of the original. Yes, the first terms are opposite. Yes, the second terms are opposite, but the third terms are the same. So this is neither the same nor the opposite, so it is neither one. To graph an odd function, I take this point, which is 0, 3, and I change the y value to the opposite, 0, negative 3. I take this point, which is 3, 0, and the opposite is negative 3, and the opposite of 0 is still 3. Let's take this point. That point is 7, negative 2. If I make 7, negative 7, the negative 2 should become the opposite, or a positive 2. So if I make the x the opposite, the y has to be the opposite as well. What happened here was the opposite of 0 stayed 0, so the y value did not change.